All right, we're in section 4.2. We're going to be talking about something called reduction of order. This is a very short section, especially compared to 4.1, which was a very large section. And we're only going to look at a couple of examples here, but this technique is going to become very relevant in section 4.3, so we're going to see it used pretty much right away. The idea in this section is we're going to be looking specifically at homogeneous linear second order DEs. And as we saw back in section 4.1, if we're going to look for a general solution for a homogeneous linear second order DE, then the goal is to find a fundamental set of solutions, which remember is a set of solutions where the number of solutions in our set is the same as the order of our DE. So this would mean we're looking for a set of two solutions specifically, and we want them to be linearly independent. If that were the case, if we do find linearly independent solutions, then we form the set of all linear combinations of those, C1, Y1 plus C2, Y2. That forms the general solution to the DE that we started with. Now, as we're going to see again in section 4.3, where we look at kind of some of the simplest cases of homogeneous second order linear equations, sometimes your solution method will give you both of these solutions at the same time. And in that case, that's fantastic. You just use those to construct your general solution. But as we are also going to see in 4.3, sometimes your solution method only gives you one solution. We only get y1, for example. And now you're left with the task of figuring out y2 so that you can have this fundamental set of solutions and wrap the problem up. So if your solution method only yields one solution like this, we need to somehow come up with a second one, and this technique that we're going to talk about is going to use our first solution to produce a second solution. And here's the underlying concept. We are specifically looking at the case of second order DEs, which means we want a fundamental set of solutions containing two solutions exactly. Now, in section 4.1, we looked at what it meant for a set of two functions to be linearly independent. In fact, let's think of it in the other context. What does it mean if a set of two functions are linearly dependent? We showed in 4.1 that this would imply that one function is a constant multiple of the other. So you could say, for example, y1 is equal to c for some constant c times y2. We want this to not be the case because, again, we want this set to be linearly independent. So in order to force this relationship to give us something that establishes linear independence between these in this set of functions, I can use this and replace that constant c with a non-constant function, which we're going to call u of x. Okay, so what's happening here is we are forcing a relationship that would guarantee that y1 and y2 are forming a linearly independent set. Because again, these can only be linearly dependent if this is a constant function, as we're seeing here. Forcing it to be a non-constant function gives us linear independence. So essentially, we're actually looking at a couple of things. One, we're going to be given a DE, and we're going to be given a solution to that DE, which we're going to be thinking of as y1. And then we're going to say, let's see if we can find a function, u of x, that I can multiply to y1, such that the result is another solution to that DE. If that's the case, and if u of x is a non-constant function, then we'll know without having to verify that y2 is also going to form a linearly independent set with y1, and we will have found our fundamental set of solutions that way. So that's the idea. Let's try this with a problem. So let's suppose that we have this DE, y prime plus 9y equals 0. And we're also given a solution, y1 equals sine of 3x. In section 4.3, we'll talk about how we could come up with this solution. But right now, we don't know how we would have found this. So we're just going to take for granted that we know a solution to this. What we want to do is find a second solution, y2 such that y1 and y2 form a linearly independent set, because that would give us a fundamental set of solutions. So again, the idea is to take the one solution we know, multiply to it some unknown function u of x, and set y2 equal to that. So here's what that's going to look like. y2 equals u times y1, which is sine of 3x. Okay? Now, in order for this function to do what I want it to do, y2 needs to be a solution to this differential equation. I'm missing a prime here. That should say y double prime. Let me fix that. So in order for this to be a solution to this, I need to know the second derivative of this. So let's figure out some derivatives now. If y2 is equal to u sine of 3x, remember u is a function of x, so I have a product of two functions of x here. That means y2 prime I would find by using my product rule. So that's u prime sine of 3x plus 3u cosine of 3x. Okay, now if I want to find y2 double prime, I'm going to have to apply the product rule in two different places. y2 double prime equals, okay, so starting here, I'm going to get u double prime sine of 3x plus 3u prime cosine of 3x, and then applying the product rule here, I'm going to get plus 3u prime cosine of 3x plus, actually no, I'm sorry, this will be a minus now, minus 9u sine of 3x. Let's combine some like terms here. I get u double prime sine of 3x plus 6u prime cosine of 3x minus 9u sine of 3x. Okay. Now, again, all I've done is I found the second derivative of the thing that we want to be a solution to our dE up here. In order for it to be a solution, I need to be able to plug this in here and get 0. So I'm going to plug my y2 in for y and my y2 double prime in for y double prime here, and then see what happens. Y2 double prime is this. U double prime sine of 3x plus 6u prime cosine of 3x minus 9u sine of 3x plus 9, this will be y2. So plus 9y2, which is the same thing as 9 times u sine of 3x, plus 9u sine of 3x. Now you may notice something interesting happening here. We get cancellation with these two terms, and it's really important. I need to make sure that's equal to 0. It's really important that we notice that we're canceling the terms that have u's in them. So that means the only place where u's are showing up are technically this u prime here and this u double prime here. So now what I'm left with is u double prime sine of 3x plus 6u prime cosine of 3x equals 0. Okay, now here's where the solution method is going to get its name from. Because there are no u's present in this equation, I get to do something kind of tricky. So let w equal u prime. I'm going to let w equal the derivative of u. If I make some substitutions here, then that u prime becomes w, and that u double prime becomes w prime. So this is w prime sine of 3x plus 6w cosine of 3x equals 0. Now we've made a variable substitution, but what that substitution has done is it's taken a second order equation and reduced it to a first order equation. First order equations are what we spent all of chapter 2 learning how to solve. So suddenly this opens the problem up to tools that we wouldn't have been able to use yet. So now this turns out to not just be a first order equation, but it's our favorite kind. It's actually a separable equation. So I would write w prime as dw dx and then separate variables. You've done enough of this up until this point. I'm going to go straight to what the separation would look like and let you verify. We're going to get cotangent of 3x dx equals negative 1/6 dw over w. Verify this. Make sure I got that correct, okay? Fill in those gaps there. Integrating both sides, that's next. The integral of cotangent of x is the natural log of the absolute value of sine. We have a 3x in there, so this is actually going to be 1/3 times the natural log of the absolute value of sine of 3x plus c equals negative 1/6 natural log absolute value of w. Okay? Now, I want to point something out here. The variable u is chosen in such a way that that it is it's the derivative of u. Okay, so in other words, we want u to be an antiderivative of w. This will work for w no matter what c is. So this is where we get to be choosy and select a value for c, because any value we use for c here will produce a solution. We might as well go with a simple value of c to make our work easier. Let's set the c equal to 0. Set c equal to 0. That just gets rid of that constant of integration, so it's not floating around and making things more complicated. Okay. Now, what's next? I want to solve for w, basically. Let's multiply both sides by -6 to get rid of that negative 1/6. That gives me negative 2 natural log absolute value of sine of 3x equals natural log of the absolute value of w. Okay, and then what we're going to do is take that negative 2, put it up as the exponent here. What this gets me natural log of, this would take a reciprocal, so it's actually cosecant squared of 3x equals natural log absolute value of w. Notice I've lost the absolute value bars here. That's because I'm squaring something now. So it's not ever going to be negative anyways. The absolute values are redundant. This implies that w equals cosecant squared of 3x. A couple of things worth noting here. First of all, I dropped the absolute value bar on my w, and I did that because really what that would have led to is w equals plus or minus this. But again, we just want w to equal u prime. And there's different choices of u that can work here. So we're going to go with whatever makes the work less cumbersome. I'm just going to assume that we're working with a positive here. It's all going to get absorbed into that constant that shows up at the end anyway, so that's okay. Now remember what w is. W is u prime, or du dx. That's equal to cosecant of 3x. If we integrate both sides, technically we'd be separating variables, moving this dx over here. That's going to imply that u equals the integral of cosecant squared of 3x, which is equal to negative 1/3 cotangent of 3x. And again, plus c, but as we've seen, it's beneficial to just let the c equals 0, because we're going to account for that constant of integration at the end. Okay, we don't need to carry it with us through all this work. I got to the bottom of my page here, so I'm going to try and use my space wisely. Come up here. Okay, so what do we do with that? Well, remember, u is the function that we are multiplying y to or sorry, we're multiplying to y1, which is sine of 3x, to get that function y2. So that means that y2 is equal to our function u, which is this, negative 1/3 cotangent of 3x times sine of 3x. That's y1. Cotangent of 3x is the same thing as cosine of 3x over sine of 3x. The denominator of the sine will cancel with this, and I'm left with negative 1/3 cosine of 3x. Now, I could just call it a day here, but remember what we would be doing with this fundamental set of solutions. Now I have a y1 and a y2. I have y1 equals sine of 3x. I have y2 equals negative 1/3 cosine of 3x. I would be multiplying some arbitrary constant to each of those and then adding them together. If I wanted to write my general solution, I could say my general solution, even though the problem didn't specifically ask for this, I'll go ahead and write it, is y equals c1 times y1, which was sine of 3x, plus c2 times y2. Now, y2 is equal to this function right here, and the first thing I see is a constant. But I'm multiplying an arbitrary constant to that, so that would look like negative c2 over 3. The negative 1/3 doesn't really matter because it's already an arbitrary constant, so we're going to think of this constant as absorbing this one and just write cosine of 3x. Okay, because that's the part that actually matters, is that cosine of 3x. This constant is absorbed into this. This would be my general solution. Okay, so even though I could write this, I could also just say cosine of 3x is my answer. All right. So again, we call that reduction of order, and the reason for that is because what we're doing here is taking a second order equation and making a specific substitution that will reduce that down to a first order equation in a different variable using that substitution. And then from there, we solve using first order techniques and get what we're looking for, that second solution to this DE. I'm going to end this video here, but in the next video, we're going to do something that we don't do a lot of, which is we're going to derive a general formula for this technique, and we're actually going to use that general formula. So that'll be part 2.